Unsupported length and effective length of column and Q index for story. Unsupported length of a column is to be taken as clear distance between the floor and the shallowest beam framing into the column in each direction at the next higher floor level. So this is lower level top, and this is upper level top, okay, and the height from top to top of the floor is 3 meters. Okay, this is our column. These are the beam falling on the column. This is x axis, this is y axis. Okay, so we can see that unsupported length Lx, okay, that is we have to take the shallowest beam as explained in the definition above. The depth of this beam over here is 600 mm and the depth of this beam is 400 mm. So out of these two we have to take the least depth for finding the unsupported length. So Lx will be equal to 3 meters minus least depth, that is shallowest beam, depth of the shallowest beam, that is 450 mm, that is 0.45 meters. So the unsupported length Lx will be 3 minus 0.45 is equal to 2.55 meters, right? Similarly, unsupported length Ly for this column will be this depth of this beam is 450 mm and this is 300 mm. So the shallowest beam is this and the least depth is 300 mm. So Ly is equal to 3 meters minus 0.3 meters, that is equal to 2.7 meters, right? So this is how we find the unsupported length Lx and Ly for the particular column. Okay, effective length of column Le is the effective length of a column for a given plane of bending between the theoretical points of inflection in the buckle configuration of the column in that plane. So this is something which we know. Okay, so Le is equal to K into L, where Le is the effective length, L is the unsupported length, and K is the ratio of effective length to the unsupported length. Okay. Depending upon the type of the column, that is no sway or with sway column, by using figure 26 and 27 we can find the effective length of a column, right? So code has given two figures which are developed by R.H. Woods, and our code is following that figures, right, for finding the effective length of column with sway and column with no sway, right? So figure 26 is helpful in finding the effective length for column with no sway, and figure 27 is helpful in finding the effective length for column with sway. Okay, right. In case of column with no sway, the value of K varies between 0.5 to 1. So we can see in this figure that when the ends of the column are fixed, then the K value is given is 0.5, and when the end of the columns are hinged, then the value of K will be 1. Okay, so code has given some standard theoretical values and recommended values for some standard cases which usually do not occur in practical fields. Okay, say when a column, the joints of a column, both top and bottom, are rigidly fixed, okay, then it is this case you have to take K as 0.1 into unsupported length L. Okay, L is the unsupported length of the compression member. Okay, so this is theoretical value. Code recommends that in such cases you have to take 0.65 L. Okay, now second case, when one end is rigidly fixed and other is hinged, in that case you have to take your factor K as 0.7. so that is what shown by this. These are all theoretical values which are obtained from this figure, right? Similarly, if both the joints are hinged, then it will be this case. K, the value of K will be 1. Okay, so the value of K is 1. Okay, but code over here code gives a recommended effective value. Okay, so when you are considering the effective length for design, then you have to take the recommended effective length, right? But these are very standard cases which we usually do not face in practical phase, right? So these are the cases for the braced column. These are the cases for unbraced column. Okay, so this the theoretical value for these cases are obtained from this figure, and for unbraced column the theoretical values are obtained from this figure, right. So moving further, for column with sway the value of k falls between 1 to infinity. Okay, so when both the joints are rigidly fixed, okay, then the value of k will be 1, and if both the ends of the column are hinged, then the value of k will be infinity, because in case of unbraced column, okay, when both the joints are hinged, then it will be unstable system, and the system will collapse. So that is why the value of k will be infinity. Okay, right. The code also suggests that the value of k in case of columns with sway should not be less than 1.2. okay, that is as per IS 456-2000. We can see over here, okay, over here, when your one end is a rigid joint and another is allowed to sway but is not allowed to rotate, okay, then as according to the graph, we have the value of k as 1, okay, but code recommends to take it as 1.2, because the value of k should not be less than 1.2 as mentioned over here, right. K should be at least 1.2. okay, that is the reason, right. Okay, in figure 26 and 27 of IS 456-2000, beta 1 and beta 2 are equal to sum of stiffness of the columns falling at the considered joint divided by the sum of stiffness of the columns falling at that joint plus the sum of the stiffness of the beam falling at that joint. Okay, yeah, beta 1 and beta 2. okay, beta 1 represents the degree of freedom at the top joint, and beta 2 represents the degree of freedom at the bottom joint of the column. Okay, we will see this detail as we move forward. Okay, we will take an example in which these things will be explained in detail. Now, coming to the stability index Q of a story. An approximate way of deciding whether a story column is a sway column or a non-sway column is given in IS 456-2000. When the stability index Q is found to be less than or equal to 0.04, then the column is designed as non-sway column. When the stability index Q is found to be greater than 0.04, then the column is designed as a sway column. Okay, so annexure E gives the formula for finding stability index Q. Okay, so I represents the Q for the ith story, right? Okay, so the formula is summation of PU into delta U divided by HU into HS. You have to find QIX and QIY, that is, you have to find the stability index Q in both the respective direction. Okay, so this is our YY axis and this is XX axis. At present we are looking towards YY axis. Okay, so this is the displacement delta 1, this is the displacement delta 2. So delta U is a story drift, that is delta 1 minus delta 2, right? So that is how you get delta U, right? Now summation of PU, this PU, summation of PU is nothing but the sum of the vertical forces in the column. Okay, P1 is the vertical forces in this column, P4 is the vertical force in this column, P3 is the vertical forces in this column, P2 is the vertical force in this column. Okay, so you have to take the sum of vertical forces of all the column in a considered story, right? So summation pu is equal to p1 plus p2 plus p3 plus p4, or summation of vertical forces of all columns in a story, right? hu is the total lateral force acting in the story. Okay, total lateral force acting in the story. hs is the height of the story, right? Okay, fine. So we will start with an example, and we will try to understand all the concepts. Okay, example: find the effective length of column 1 2 3 4 in 3D frame shown below, right? So this is column 1, this is column 2, this is column 3, this is column 4, right? Okay, so this is our first story, this is our second story, and this is our third story. Okay, now a question comes in our mind: what value of pu and hu should be taken when we are considering number of load combinations, right? So whichever load combination is giving you maximum story drift, okay, that then for that combination the corresponding pu and hu has to be taken in account for finding the value of q, that is, right, stability index q, right? So we are assuming that in our case this is the condition which gives the maximum story drift. So we are considering udl is equal to 50 kilonewton per meter acting on all the beams. This is y axis, this is x axis, okay, and lateral forces are acting at the nodes. At first floor 35 kilonewton is acting, at second floor 50 and 50 kilonewton is acting, at third floor 100 and 100 kilonewtons are acting. Okay, so for this loading we get this sway diagram of the frame, right? So as we are considering that this combination is going to give us the maximum drift, so we are going to consider the displacement in this direction, right? Because there are no lateral forces in this direction, the lateral forces are all in this direction, right? So the lateral displacement over here is 0.0095, this lateral displacement is 0.0065, this displacement is 0.0026. okay, this is all obtained from the analysis of the frame, okay, first order analysis. Okay, so now moving further, now coming to the sizes of the member size. Okay, size of all columns in this 3D frame are 500 mm by 500 mm. All columns are of size 500 by 500 mm. Okay, the sizes of all beams along y axis are 250 by 550, right? Y axis, all the beams in this direction on all the floors are of size 250 mm width and 550 mm depth. Okay, and the length of the beam is 5 meters. Okay, size of all beams along x axis are 250 by 350. Okay, this is x. So all the beams in this direction on all the floors are of size width 250 mm and depth 350 mm. Okay, and the length of beam is 3 meters. Okay, fine. So find the moment of inertia of column C1 C2 C3 C4. Simple. So this is it. Moment of inertia of beams along y axis, so this is it. Okay, and moment of inertia for beams along x axis is found to be this much. Okay, now summation pu of first floor, right? So how do we get that? Everything is obtained from the analysis. Okay, this is our first story, right? And we want to find the summation pu for the first floor. So we will have to add all these blue vertical forces which are acting in the column. Okay, the summation of all these forces, vertical forces in the column, will give us pu first floor, that is 5100 kilonewton, PU summation of PU second floor, that is we have to take the second story. Okay, so this is our second story, right? So all these black arrows that are the vertical forces in the column, okay, you have to sum them up, and that will give you some PU second floor, that is some PU second floor, that is 3400 kilonewton. Now some PU for the terrace floor level, that is third story. Okay, so this is our third story. So add all these black arrows. Okay, these are the vertical forces in the column. Okay, you have to sum them up, and this will give you some PU for the third story, that is terrace level, 1700 kilonewton. Okay, now sum of lateral force, total lateral forces acting on the first floor. So we know that on the first floor it is 35 plus 35 plus 35, so that is equal to 105 kilonewton. On second floor it is 50 plus 50 plus 50, that is equal to 150 kilonewton. And third floor it is 100 plus 100 plus 100, so that is equal to 300 kilonewton, right? Now we have to find HS. So HS is given to us. All the story height are 3 meters, right? So HS is equal to 3 meters for all the stories, story, third story, second story, and first story. Okay, now we have to find the story drift. Simple. Column C1. Column C1 is on second floor. So the displacement at the top is 0.0065 and at bottom is 0.0026. So 0.0065, 0.0026. So this minus this is your story drift, that is equal to 0.004. Now C2. Okay, C2 is this column. So this is your first story. The displacement at this point is 0.0026 and displacement over here is 0. So your story drift will be this minus this is equal to 0.0026. Now C3 and C4, they fall on the same story, that is third story. Okay, so over here the displacement at top is 0.0095 and bottom is 0.0065. So that is what we have taken, 0.0095, 0.0065. So this minus this is equal to 0.003. So the story drift for this two is 0.003. Okay, so now we have everything with us. We have some PU, we have HU, we have HS, we have delta U. So we can find the story index Q for each story. Okay, so this is our generalized formula. So these are the story number. This is third story, this is second story, this is first story. Let me show you the 2D diagram. First story, second story, third story. Okay, fine. So this is third story, this is second story, this is first story. Okay, sigma PU. Okay, we have found this for first, second, third. We have already found it from the analysis, so which we have kept over here, right? Now story displacement. Okay, so story this is how we got the story displacement from the analysis. 0.0095, 0.0065, 0.0026 and 0. So which we have kept over here. Okay, 0.0095, 0.0065, 0.0026 and 0. Now story this is story displacement. Okay, and this is story drift. Okay, all right. So story drift is this minus this is the third floor story drift. Okay, and this minus this is this story drift, this minus this is this corresponding story drift, right? Okay, HU again we have found from the load given on the frame. Okay, and HS is the height of the story, which is constant, 3 meters, 3 meters, 3 meters. So we all know everything. Okay, so we can find the stability index Q for each floor. So for third floor, Q is found to be 0.0056, which is less than 0.04. That means all the columns on this story will be designed as a non-sway columns, right? Over here the Q index is found to be 0.029, which is less than 0.04. So again all the columns on the story will be designed as non-sway columns. Okay, and over here, that is first story, the Q index is found to be 0.042, which is greater than 0.04. So all the columns in this story will be designed as sway columns, right? Okay, maximum allowable story drift as according to code is 0.004 into HS. HS is 3, which is equal to 0.012. Our maximum story drift is 0.0039, which is less than 0.012, so it is safe. If this condition was not satisfied, then you will have to increase the story stiffness, right? Now C1 falls on the second story, okay, column. So second story, all the columns are to be designed as non-sway column, so it will be designed as a non-sway column. Column 2 falls on the first in the first story, and in first story all the columns are to be designed as sway column, so this will be designed as sway column. Column 3 and 4, they fall on the third story, and the third story all the columns are to be designed as non-sway columns, so this too will be designed as non-sway column. Okay, fine. And now the next step is we will have to find the unsupported length of column, that is Lx and Ly, right, for C1, C4, C2, C3, right? So C1 over here, this is our y axis, this is our x axis. So in y direction we have beam of depth 550 mm on this side, 550 mm on this side. So both the beams are of the same size, so the shallowest depth over here in this case will be 550 mm definitely. So Lx will be equal to the height HS is 3 meters. So 3 meters minus 0.55, right? That is equal to 2.45, right? So as in case of C1, C4, C2 and C3 in y direction, the beam dimensions are the same. Okay, so that is why the Lx, unsupported and Lx for all the 4 columns will remain same. Okay, similarly Ly, okay, the beam depth is 350 over here also and over here also. Okay, so the shallowest depth, this depth is 350, so Ly will be equal to 3 meters minus 0.35, 3 meters minus 0.35, that is equal to 2.65. okay, and this will again remain same for all the 4 columns, because the beam in in x direction, the dimension of the beam in x direction on all these 4 columns are the same. Okay, 350 mm, 350 mm, 350 mm, 350 mm, right? So this is how we find the unsupported length Lx and Ly for column C1, C2, C3, C4, right? Now we have to find the stiffnesses. Okay, so beta 1 and beta 2, as explained earlier, beta 1 is the freedom of freedom to rotate, you can say. Beta 1 represents the degree of rotation, okay, that is for top joint, and beta 2 represents the degree of rotation for the bottom joint of the column. Okay, so that is what has been tabulated. Okay, right, beta 1 and beta 2, we can see the graph. This is beta 1, this is beta 2. Okay, fine. So this are the formula of beta 1 and beta 4 or beta 2 for column with sway, and this the formula for beta 1 and beta 2 for column with no sway. Okay, formula is same, only thing is this multiplying factor is changing. Okay, the multiplying factor, which is multiplied with the stiffness of the beam, okay, over here is 1.5 and over here it is 0.5. Otherwise everything is same. So let us try to understand what is this K, what is Ku, what is KBT, what is KBB, what is KCB. Okay, K represents stiffness. Okay, so let us take column C1, right? Okay, we want to find the effective length of C1. Okay, so this is considered as the column under consideration. Okay, so K is the stiffness of this considered column. KU is the stiffness of the column above the considered column. KCB is the stiffness of the column below the considered column, right? Okay, so C1 has two joints. This is top joint, this is bottom joint. Okay, so the summation of the stiffness of the beam falling at the top joint, right now I am considering only one direction, that is YY. So I'm considering only two beams are falling on the top joint. This is one beam, this is another beam. Okay, so the stiffness of this beam falling at the top joint is known as KBT. Okay, beam at top. And similarly, these two beams are falling at the bottom joint, so the stiffness of this beam falling at the bottom joint is known as KBB, that is beam at bottom, right? Okay, so we will take the individual cases. Okay, so first we will take this direction, and then we will take this direction, right? So this direction, in first when we take this direction, we will get we will get the effective length LEX, that is the effective length of column C1 in this direction. When we take this direction, we will get LEY, that is effective length of column in this direction, right? So this is how we find beta 1 and beta 2. Okay, so these are the formulas. So first we will find the stiffness. Okay, so for all the columns, because all the columns are of same size, 500 by 500, so K is equal to KU is equal to KCB, right? The stiffness is found to be this much. As all beams along YY axis are of size 250 by 550. Okay, so beam stiffness of beam falling at the top joint and stiffness of the beam falling at the bottom joint of the column will be the same, because the size are the same. So this is found to be this much. And as all the beams along XX axis are of size 250 by 350, so this is found to be this much, right? So once you know all these values, put these values over here and you can get beta 1, beta 2. Okay, but these calculations are very lengthy. Okay, so you can always make an program which can make your life easy. So we will try, all these values are found by manual calculation using these values and these formulas. Okay, but we will try to find this value and make our job easy through software, right? So first we will take column C1. So C1 is a non-sway column. Okay, fine, right? So let us see in the figure. Okay, C1. Okay, this is the considered column for which we want to find the effective length, that LEX and LEY. Okay, so we can see that above this considered column there is a top column, there is a bottom column. Okay, and at now we are considering YY direction, right? So there are two beams falling on the top. This top joint of C1. One beam is falling from here, another beam is falling from here. Similarly, these are the two beams falling at the bottom joint, right? Oh, right. So we know the dimension of this column, it is 500 by 500. We know the dimension of this column, it is 500 by 500. We know the dimension of this column, it is 500 by 500. We know the dimension of this beam, it is 250 by 550. We know the dimension of this beam, it is 250 by 550. We know the dimension of this beam at the bottom, falling on the bottom joint, is 250 by 550, again 250 by 550. We know everything. Okay, so we just have to give the beam width and the beam depth and the column width and column depth in the program, which we will give, and we can directly get the values of beta 1, beta 2, and can find K from the graph. Okay, so let us use the program. Okay. Right. So this is our considered column, right? This is our considered column. This is our considered column C1. Okay, this is the column above the considered column. This is the column below the considered column. This is the beam falling at the top joint, that is it is this beam. This is our top joint, it is this beam, and this beam is this beam. Similarly, beams falling on the bottom joint from here and from here, so we can see. So beam falling at the bottom joint here and here, right? Okay, so now we just have to give the width and depth of all these members. Okay, but we know that column C1 is no sway column, right? So we will have to select this graph. Okay, now let's start giving the value, right? So column width is 0.5. Okay, 0.5, press tab. Sorry, press tab. 0.5 is the depth, press tab. Height is 3 meters. Okay, now width of this beam is 0.25. Depth of this beam is 0.55. Press tab. Width of this beam is 0.25. Depth of this beam is 0.55. Width of this column is 0.5. Depth of this column is 0.5. Height is 3. Width of this column is 0.25. Width of this beam, okay, not column, beam. Width of this beam is 0.55. Width of this this is depth, sorry, this is width, this is depth. Width of this beam is 0.25 and depth of this beam is 0.55. Okay, width of this column is 0.5. Depth of this column is 0.5 and height of this column is 3. Okay, okay, now length of this beam. Okay, length of this beam, we know this is 5 meter and this is 5 meter, so we will give 5, okay, and 5. Okay, now calculate. So we get the point, we get beta 1 and beta 2. This is 0.833. So that is what we get over here, right? This is a case we are taking beam along y axis, right? So for C1 we get it's a non-sway column, it is 0.833 and 0.833, right? So when you find the ordinate on this graph, this is for non-sway column, right? Then you get the value of K equal to 0.875. We can see this figure, right? We get this point. Okay, so this is graph 11. So all the value of K on this graph 11 is 0.85. This is graph 12 and the value of K on graph 12 is 0.9. Our case is in between these two, so we will take it as 0.875. Okay, simple. So that is how we got the value of K. So we know LEX by LX, right? We are finding LEX, that is in YY direction, right? So LX we have found. LX is the unsupported length. Okay, so we know the unsupported length LX is equal to 2.45 for column 1. Okay, so that is what I have taken over here. LX I have taken as 2.45. So LX into K is equal to LEX. So that is equal to 2.1437, right? So what we have obtained, let me explain you on the figure, that we have found the effective length of C1 in this direction, that is along YY axis, right? Now we want to find the effective length LEY along XX axis, okay, for the column C1. Simple, everything remains the same. Okay, only thing is that in this direction the depth and the width of the beam were 250 and 550. The width was 250 and depth was 550. Width was 250 and depth was 550 over here. Now we are taking this direction, right? So over here the beam size changes, right? The width is 250 and depth is 350. Width is 250 and depth is 350. Similarly over here also, at bottom joint also, width is 250 and depth is 350. Width is 250 and depth is 350. And the length of the beam now is 3 meters and 3 meters, right? So that small change we have to make in the input, and that will give the value of beta 1 and beta 2 for the beam along axis, right? So simply change the depth. So this is going to be this is going to be 0.35, right? Press tab. Width is the same, depth only changes, so this is again 0.35, right? There is a top column. The dimensions for the column will not change, okay, because they remain the same. Only the dimensions of the beam will change. Over here again it will be 35, and over here again the depth will be 0.35 meters, right? And the length of the beam will change. That is, now it is 3 meters and it is 3 meters, right? Simple. Just calculate, okay? So we get beta 1 and beta 2 is 0.921. So let us see the case for beam along x-axis, okay? Taking beam along x-axis, so C1 non-sphere column, we get beta 1 is 0.921, right? So this is exactly which we get from the software. So software can make your life very easy and save a lot of time, okay, and a lot of calculations. From here we can see that this point falls over here, that is graph 13, that is 0.95. Our is little bit inside, so we'll take k value as 0.94, which I have taken over here. K is 0.94, right? Now Ly is unsupported length in the table which we have already found. C1 Ly was found to be 2.65, so we'll take Ly as 2.65, right? So this into this will give you Ley. So that is equal to 2.491. So what is Ley? So Ley, which we have found, is the effective length for column C1 in this direction, that is along XX direction, right? So this is how we found Ley and Lex for C1 column. Similarly, we can find for C4, C2 and C3. We'll take another case, the C2, right? Now let us find Ley and Lex for C2. Now in case of C2, when this is the considered column, you have a column at the top, okay, you don't have any column at the bottom. So for the members which are not present, okay, you have to give width and depth equal to 0, definitely, okay. We only have one beam falling at the top joint. There is no beam on this over here, and there is no beam at the bottom. Now we are again considering y axis, only y axis, right? So there is only one beam falling at the top joint, and there are no other beams, right? So, and there is no bottom column, okay. So we'll change the input data similarly, okay. Now the size of this beam is 250 by 550, and the length of this beam is 5 meters, right? So there is a top column, so this will remain, okay. There is a beam on this side, okay, that is this beam, they're falling at the top joint, okay. So this is the considered column C2, this is the top joint, this is bottom joint. We have a beam over here, we don't have any 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 column over here. So all these values we will turn it to 0, right? Okay. The only thing we have to change over here is the depth of this beam is 550 mm. So let us take 0.55, right? Now this, there is no beam over here, so we'll turn this to 0. Okay, there is no beam over here, so we will turn this to 0. Okay, right, fine. This column is our considered column. The dimensions are the same, that is, all columns are of 500 by 500 mm, so there will be no change over here. Okay, there is no beam over here, so this will be 0. There is no beam over here, this will be 0. There is no beam over here, so this will be 0. There is no beam over here, this will be 0. There is no column over here, so this will be 0, right? No column over here, so 0, 0, right? Okay, fine. Now the length of this beam is 5 meters. Okay, so we'll write 5 over here. Okay, there are no beams on this side, so 0, right? Simple. Now please remember that C2, column C2, we are seeing C2 falls on the first story and it has to be designed as a sway column, right? So we will have to change our graph. So change your graph. Okay, now just click calculate. Okay, so we get beta 1 and beta 2, and let us check it with the manual results. Okay, beta 1 and beta 2 we get for considering the beam along y axis. Okay, column C2, beta 1 is 0.769 and beta 2 is 1. Beta 1 is 0.769 and this is 1, right? Fine. And we get this value as 0.35. Okay, that is what I have taken. K, value of K is taken as 0.35. Okay, so when you plot this beta 1 and beta 2 over here from this graph, you will get the value of K. Okay, fine. So once we know the value of K, we know LEX for column 2. Sorry, we know LX. LX is the unsupported length, right? Unsupported length for LX, unsupported length LX for C2 is 2.45. Okay, so that is what we have taken over here, 2.45 into K, that is equal to 8.575. that is your LEX. Okay, so let us try to understand on the figure. LEX is the effective length of this column 2 to be taken in design along y axis. Okay, similarly now we have to find LEY, right? That is effective length of C2 in this direction. Okay, so when we are considering this direction, then we will have to consider this beam. Okay, everything remains the same. Over here also at top only one beam falls. The size of this beam is 250 by 350 mm and the length of this beam is 3 meters. So only this minor change has to be made in the program. Okay, so turn this to 0.35 meters. Okay, everything remains the same, and just turn this length to 3 meters. Okay, because the length of the beam is 3 meters, right? Simply make this change and calculate, right? So we get our beta 1 as 0.886 and beta 2 as 1. Let us see the theoretical value which we obtained by manual calculation. Okay, so we got 0.769 and 1. Okay, that is what we got. We have to see along x-axis, right? Along x-axis, right? So C2 we got 0.886 and beta 1 we got as 0.886, beta 2 we got as 1. That is what we got from the program, 0.886 and 1. Okay, so this is found to be 4.5 K. Okay, so K I have taken as 4.5, right? Okay, once you know K, you know Ly. Ly we have already found, unsupported length Ly for C2 we have already found in the table above. Ly for C2 is 2.65. Okay, so taking that 2.65 over here into 4.5, the Ley, effective length Ley, is found to be 11 0.925. So that is the effective length of column C2 along x-axis. Okay, this is our x-axis. Okay, so 11.925 is the effective length which we obtained. Okay, this is LE y, right? This is LEY, this is LEX. So this is how we found LEY and LEX for column C1 and C2. Okay, similarly you can find for C3 and C4 also, right? Okay, once you find the LEX and LEY for all the columns, then simply LEX divided by the lateral dimension and do LEY divided by lateral dimension. Is if this ratios are found to be less than 12, then you can design it as a short column, or else you will have to design it as a slender column. Okay, so please visit website mmsprogramcivil.com for all the videos in PDF. I hope you must have found this video useful. Okay, so thank you very much.